All right, welcome back everybody. Let's go through our first ANOVA example. I'm assuming that you're looking at a blank sheet in front of you, example one that's not actually completed. And what you should do is just fill it in as we go. As I walk through the steps, you should work out the example. So I took all the prep work that we did and I replicated that right here. So now that we have all that prep work done, we have all the information that we need to go through all of the formulas and eventually compute our F ratio. Remember what we're trying to do now? We're trying to determine if the temperature of the room has an effect on how much these people learned. So in other words, I'm trying to determine if the variability we see here between these groups is above and beyond the variability that we see simply within these groups. All right, so let's start at step one. Remember, we always have two competing hypotheses, a null hypothesis and an alternative hypothesis. The null hypothesis is going to state that the populations that these three groups represent, the populations that these three samples represent, are equal. There's no differences. So I put down that the population mean for the memory scores for the people in the 50-degree room is equal to the population mean memory scores for the people in the 70-degree room, which is equal to the population mean memory score for the people in the 90-degree room. So in other words, temperature of the room has no effect. The alternative hypothesis is simply at least one population mean differs from another. If we find a statistically significant result, we would find that at least one group differs from another group. And then later on, if that's what we find, we'll learn how to do post-tests to figure out which groups differ from other groups. All right, that was step one. Let's move on to step two. Remember, step two is always figuring out how much evidence do we need to reject the null hypothesis. In other words, where is our critical value? I need to figure out where the critical region is. In other words, I need to figure out where we can mark off the most extreme 5% of the F values. Remember that F distribution keeps changing shape based on the number of people we measure, based on the number of groups that we're comparing. So we need to compute degrees of freedom between groups and degrees of freedom within groups. And then based on those degrees of freedom values, look up a critical value in an F table. We're going to be using an alpha of 0.05. So we've got a little bit of room over here in step three to compute degrees of freedom. I've got degrees of freedom between right here. Remember, degrees of freedom between equals k minus 1. That's the number of groups minus 1. We clearly have three groups here, so 3 minus 1 equals 2. So we have 2 degrees of freedom between groups. Degrees of freedom within groups is based on the number of people overall minus the number of groups. Remember, the number of people overall right here is 15 people. So in this case, 15 people minus 3 groups equals 12 degrees of freedom within. Remember, sometimes we call that error, degrees of freedom error. Within and error are the same term in general when we talk about analysis of variance. Although we don't need degrees of freedom total, we could very easily compute it right here. It's based on the number of people overall minus 1. We had 15 people overall, minus 1 equals 14 degrees of freedom. One reason why I really like to compute that is because then it gives me a check of my work. Degrees of freedom between plus degrees of freedom within should equal degrees of freedom total. Another way to help kind of organize our thoughts is to fill out the ANOVA summary table, the ANOVA source table as we go. So I have one for this example right here. And again, mine is already filled in, but you can fill yours in as you go. So I skipped over to the degrees of freedom column and I put in 2 degrees of freedom between, 12 degrees of freedom within, 14 degrees of freedom overall. So you should fill that in now as well. Our goal is to get all this information filled in so that we can ultimately compute the F ratio. In general, we're starting at the left and moving to the right, but because in step 2 we need to figure out the critical value, it makes sense to compute degrees of freedom first. All right, let's go ahead and go back to our example. We now know that we have 2 and 12 degrees of freedom. Remember the way that we phrase that, 2 and 12, is always based on degrees of freedom between first and degrees of freedom within second. So I've written it this way, 2 and 12 degrees of freedom. And I know there's a comma in between there. That's the way we always write it, but we read it as 2 and 12. All right, we're using an alpha of 0.05. So I'm going to find my F table based on an alpha of 0.05. It says right here, critical values for the F distribution alpha equals 0.05. You have access to this table. We have 2 and 12 degrees of freedom. So I'm going to look at 2 right here. I'm going to find 12 right here, and then I'm going to find where they converge. Looks like they converge right here. So it's kind of hard for me to highlight that. There we go. 2 and 12 degrees of freedom. So the critical value is 3.89. So let's come back to our example. And you can see I marked it off at 3.88. The table that I looked at was just a little different. So again, just go ahead and consider that a typo and write in 3.89 for your critical value. Unfortunately, some tables differ by just a very small amount. No big deal either way. So go ahead and write in 3.89. That'll be consistent with your table. All right, now we know how much evidence we need. Now let's figure out how much evidence we have. So back to step 3. Here I have some room to compute sum of squares. And again, as we look at this summary table, we see we need sum of squares between groups, sum of squares within groups, sum of squares total. We need this stuff before we can compute this stuff, because this stuff is based on this stuff right here. So that's why it makes sense that we start toward the left and then we move toward the right. So let's compute sum of squares between groups first. So of the 3 sum of squares we're going to compute, here's the formula for sum of squares between groups. So it says sum up a series of these fractions. These are based on totals. So remember the total values we computed for each group. It says take the total, square it, and divide by the number of people in that group. The sigma is telling us to do that for each group. Once we get through each group, then we're going to subtract the grand total squared divided by the overall n, the overall number of people that we measured. So let's walk through it. I'm going to come over here and find my first group and the first total. It's a 5. According to the formula, I need to take 5 and square it. So here's 5 squared divided by the number of people in that group. And you can see I have 5 people in each group. So I have 5 squared divided by 5. The sigma is telling me to add that to the exact same fraction that we complete for the next group. So the next group has a total of 20. So now we're going to take 20 squared and divide by the 5 people in that group. And then we will add to that the information for the third group. The third group has a total of 5, so we're going to take 5, square it, and divide by the 5 people in that group. Do you see how now we have exhausted the sigma? We've gone through all the totals. We have none of them left. So I'm going to move on with my formula. It says minus, so I say minus right here, grand total squared divided by n. The grand total is 30, so we just take 30 squared, divide by 15. We have 15 people overall, 5 people in each of the 3 groups. So that's it. At this point, all we need to do is work it out. I'll work this one out real quickly with you. So I'm going to take 5, and I'm going to square it. I actually have, I do have a square key. 5 squared divided by 5 equals. All right, so that first fraction reduces down to 5. Let's look at that second fraction. Now we need 20. Let's go ahead and square it and divide that by 5. That equals 80. Next fraction, we're going to take 5. We need to square it. We're going to divide that by 5. That equals 5. And now we're going to look at this last fraction. We're going to take 30. We're going to square it. And we're going to divide that by 15. So that equals 60. All right, so now we need to take 5, add to that 80, add to that 5, and then subtract 60. So sum of squares between groups equals 30. All right, so we'd move over to our source table, fill in 30, look and see what we want to compute next. We want sum of squares within, otherwise known as sum of squares error. So sum of squares within just says take the sum of the sum of squares for each group. And remember, we took the time to compute sum of squares for each group. All we need to do is add them up. 6 plus 6 plus 4 equals 16. Come back to our source table, fill in that value. Now, do you see how we can already predict what the sum of squares total is going to equal? If sum of squares between is 30 and sum of squares within is 16, I'm predicting that this is going to equal 46. So sum of squares total provides us with an opportunity to check our work. So here's the formula for sum of squares total. It says take the sum of x squared. And remember, we took every single value, we squared each of those values, and we added them up. And we found the sum of x squared was equal to 106. We have to take that value and then subtract this fraction. So we have 106 minus 30 squared divided by 15. That gives us 106 minus 60, which equals 46. And that's exactly what we were expecting to find. All right, so I'm feeling good right now. Everything's making sense. It's fitting together. Now, when it comes to all the things we need to compute before we get that F ratio, this stuff is all done, and all that's left is based on things that are already in this table. So to compute the mean square between groups, in other words, variance between groups, we'll take sum of squares between groups and divide by degrees of freedom between groups. So 30 divided by 2 is 15. So that's easy enough to see, and I've got that worked out right here. 30 divided by 2 is 15, mean square between groups. The next thing we need to compute is mean square within groups. So we'll take sum of squares within the groups and divide by degrees of freedom within the groups. Sum of squares within the groups is right here with 16. And we need to divide by the degrees of freedom within, which we computed right over here, is 12. So 16 divided by 12 equals 1.33. So let's go to our source table. And right there, we put in 1.33 for mean square within groups. Well, now we have the two variance values that we need to compare essentially in a ratio to compute F. F is just the ratio of between group variation over within group variation. So let's just take a look. When we compute F, we have mean square between over mean square within. So we're left with 15 divided by 1.33, which equals about 11.28. So of course, now we need to compare our obtained F value, 11.28, with our critical F value, which we agreed was 3.89. Clearly, 11.28 is beyond 3.89. So that basic question comes up, are we in the critical region? Yes, we're in the critical region. Remember, all the follow-up questions should be answered in the same way. And the next follow-up question would be, should we reject our null hypothesis? Yes, we should reject our null hypothesis. It's very unlikely to find this F value just by chance. So on your sheet, go ahead and cross out that null hypothesis and then check off the alternative. We are going to embrace that alternative hypothesis. So we now believe, let's just take a look at that and interpret it. We now believe at least one population mean differs from another. Now, when we just look at these means down here, we can get a sense of what's going on. I mean, I have a sense that when people are in a comfortable room, they learn more information than people in a cold room or a hot room. But this is just the overall analysis of variance. We call it the omnibus test. It essentially just means the overall test. Omnibus is O-M-N-I-B-U-S. This overall test is just looking to see, are there differences? Do differences exist between, in this case, these three groups? And we found, yes, differences exist. Now, eventually, we will need to do post-tests to figure out which groups actually do differ statistically significantly from each other. So at this point, we ask ourselves another question. Do we have statistically significant results? Yes, we do have statistically significant results. We used an alpha of 0.05, so our results are statistically significant at the 0.05 level. We also ask another follow-up question just to make sure we understand the big picture. Is it possible that we're making a type 1 error? Yes, it's possible that we're making a type 1 error. Remember, over the long run, using this type of strategy that we're using, we will make type 1 errors about 5% of the time because we're using an alpha of 0.05. All right, let's go ahead and interpret our results at step 4. So this is about the best that we can do right now because we're just doing this overall omnibus test and we have not yet done post-tests. Clearly, the F ratio is in the critical region, and it's very unlikely to find an F value of 11.28 if the null hypothesis is true. It makes us question the null hypothesis, and ultimately we reject it. So in everyday language, what did we find? We can say statistically significant differences in memory exist among the groups. Remember, another thing we need to do is now summarize how this test would look in a journal article. We didn't do a z-test, we didn't do a t-test, we did an f-test. So we're going to begin this little phrase right there with an f. Sorry, every time I move that mouse a little too far down the screen, Adobe Acrobat wants to stick up those little tools for me. So we begin with f, and then in parentheses, we have to put the important degrees of freedom between and degrees of freedom within, because we used those degrees of freedom to find the critical value. So we have an f in parentheses with 2 and 12 degrees of freedom. So 2, 12 degrees of freedom. F with 2 and 12 degrees of freedom was equal to 11.28. That was our obtained F value. And the probability of finding that value just by chance is very small. The probability is less than 5%. And remember, you can ask yourself if you get confused by that. You can say, well, where was my value? Was it in the critical region? Yes, it was. That critical region is really small. So the probability should be associated with a small value. Well, p less than 0.05 is a small value. The final thing we need to do here is compute the measurement of effect size. Now, we can't compute Cohen's d. We've relied on Cohen's d for a long time, but Cohen's d is based on computing one difference. And we've got 3 different groups here. There are several different differences we could compute. So what we're going to compute as a measurement of effect size is known as eta squared. So down here on the bottom of the page, you see a Greek letter. It kind of looks like an N. It's a Greek letter eta, E-T-A, eta squared, E-T-A. And it's very, very easy to compute, a little bit harder to interpret, but we're going to get used to it because we're going to practice it. Eta squared is computed just by taking the sum of squares between groups, so right there, 30, and then dividing by the sum of squares total. Now remember, I've mentioned so many times in our class that sum of squares is just the basis for variability. So if you think about it, we're taking essentially the variability between groups and seeing how much variability there is between groups as a proportion of the total variability. So in this case, we took 30 and we divided by 46. So we found 0.65. It's essentially 65%. So here's how we would interpret this, and you should write it down. We can say that 65% of the variability in the memory scores can be explained by the temperature of the room. So you can see what this measurement is telling us is the proportion of variability in our dependent variable, the memory scores, that can be explained by our independent variable, the temperature of the room. It's the proportion of variability in our dependent variable, the memory scores, that can be explained by our independent variable, the temperature of the room. So that's a mouthful. That's going to take a little bit of practice, but we'll get plenty of practice. 65% of the variability in the memory scores. So 65% of the variability that I see in these scores can be explained by which room they were in. So of course, the more variability I can explain by the temperature of the room, the stronger the effect of the temperature of the room. And that's actually a relatively large effect size. Let me go to the next page here. I filled in the entire ANOVA summary table, the source table, but I want to draw your attention right here. Eta squared is essentially defined for you, and it also shows a breakdown of like what's small, what's medium, and what's large. And you can see an eta squared value of 0.65 is pretty darn large. Now, some people prefer computing what's known as omega squared, looks like that W down there, instead of eta squared. Omega squared is just really a modified version of eta squared. A lot of people think it's less biased, and I think that's true. It is probably less biased. But you can see the formula is a little bit more complicated. And later on, we're going to be using measurement of effect size like R squared and phi squared, and they are interpreted exactly like eta squared. This is why I like to stick with eta squared. It's simply more easy to compute, it's very easy to interpret, and it is similar to other measurements of effect size that we use later in the semester. So we're going to stick with eta squared. That, my friends, was our first ANOVA example. In the next video, we'll go through a second example, And here's the good news. It's just like the first example. Once you can master one example, you can master any example. There's a lot of computation involved in the analysis of variance. We need to compute 9 things to get to that F ratio, but we have formulas. The computation isn't difficult. It just takes a little bit of practice. I find that most students master it. And on this next exam, when we actually have to compute ANOVAs, it provides you with a good opportunity to show what you know. So take some time to practice these. If you have any questions, reach out and let me know. Take care. I'll see you in the next video.